This is the presentation for our Nanoelectronic group project. So our team member have Chok Sheng, Koay Hong, Yap Yoon Heng, and me myself, Chii Heng. So the introduction for the presentation is to introduce what is the MOSFET. So the MOSFET stands for metal oxide semiconductor field effect transistor. So it is used to control the current flow and amplify the electronic signal in the electronic devices. There are 4 terminals on the MOSFET, so which are known as gate, source, drain, and body. The MOSFET also work in 2 modes, which are depletion mode and enhancement mode. So the first effect that we observe on the MOSFET is short channel effect. Short channel effects will occur when the channel length of the MOSFET is close to the depletion layers of the drain and source junction. In this situation, the behavior of the MOSFET is out of the expectation, and this undesired effect is creating the huge impact based on the reliability and modeling of the performance. The physical phenomenon provoke short channel effect are the decrease threshold voltage and the limitation of the electron drift characteristics in a short channel effect. So there are 4 short channel effect can be classified. So the first one we are known as drain induced barrel lowering, which are also known as DIBL. So this DIBL is also referred to the reduction of threshold voltage of the transistor at high drain voltage. Next is the surface scattering. So this surface scattering is an effect that reduces the electron mobility and causing the current flow in MOSFET to be reduced. Then is the impact in ionization. This impact ionization will cause the collision of high energy electrons, which cause the holes to be dislodged to a negatively charged substrate, which causing the substrate current to be induced. The last is the hot carrier effect, which will cause the accumulation of electrons at the outside, which causing transistor to aging.
Yeah. Okay. So these are
Next, my teammate Chok Sheng will continue the presentation on simulation result.
Okay. Yeah. So these are the simulation results we obtained by using NanoHub. This IDVG and IDVD characteristic are obtained by simulating each device by adjusting different parameters based on the specification given. Yeah. Then next. Yeah. So for VTH, we obtain it when ID is equal to 1 times 10 power negative 6 ampere. And for the next is I off. I off value we obtain when VG is equal to 0 watt. And lastly, the value of I on is obtained when VG is equal to 1.0 watt, which is the Vmax. Yeah. Next. Yeah. So this is the surface charge versus VG characteristics graph we plot. Yeah. Next.
All right. All right. So continuing on, I will explain the comparison that we made together to device 1 and device 2. In this case, we will compare the ID and VG graph to between device 1 and device 2. As you can see here, device 2 reach average saturation level, which is faster than device 1. However, what does this mean? That is that device 2 have a lower threshold voltage than device 1. So, so what does this mean is that device 2 does turn on faster than device 1. So is that a good thing? Not exactly. This means that device 2 have a higher off current. This is not a very good trait. This is not a very good trait to have for a MOSFET. So in this case, it does means that device 2 have a lower threshold voltage but higher off voltage, and device 1 have opposite. It's just a design trade-off. All right, continue on. Okay, but what you see here when we compare the ID IPD graph between device 1 and device 2, you can see that the most significant difference between device 1 and device 2 is the fact that at device 2, during when the gate voltage is 1.2 volt, you can see it break off at around at very early voltage. This means that device 2 when during device 2, when gate voltage is 1.2, you have exceeded device 2 threshold gate voltage. This has caused it to break down and destroy its gate oxide layer. This is a very huge issue for MOSFET, as gate voltage 1.2 volt breakdown is a very low breakdown voltage. This is unacceptable. So if we want to solve this issue, we have to increase the oxide layer to make it harder to puncture, or just increase the substrate doping or concentration. All right, continuing on. All right, so continue on. This one is the IDBG graph for the comparison between device 3 and device 1. It have the same effect as device between the comparison for device 2 and device 1. However, this over here have a huge difference, is the fact that when you compare it, the threshold voltage is too low. It's too low, is lower than zero, is lower than zero. This that MOSFET, the MOSFET is not acting as a gate at all. It is just in some way you can consider it a one that's in peak current, but it's not a good gate as it's not covering everything up. So how do we solve this issue? The way we can solve this issue is by increasing the channel length or increase the substrate doping concentration. All right, continuing on. For this, we put it know that device 3 have a lower voltage threshold, gate threshold. However, this is already observed on IDBD graph. We just put it up so that we can show you the difference between two of them. All right. So continue on to the next person.
So we can observe short channel effects throughout this simulation. So short channel effects can be categorized to DIPL, surface scattering, impact ionization, and hot carrier effect. The first one is a DIPL. The formula for the DIPL is the difference between gate voltage divided by difference between drain voltage. Based on the calculation, we observe that device 1 has the lowest DIPL, while device 3 has the highest DIPL. Next. So what I can say that is, if the DIPL is higher, meaning that your channel length is lower and your leakage current will be higher. This is because as drain voltage become larger, it will widen the drain depletion region and weaken the potential barrier faced by electron and holes. The second one is surface scattering. Since we have device 3 with a very short channel length, the electric field created by the drain voltage will become stronger. In order to compensate the strong electric field, the vertical electric field created by the gate voltage need to be increased. Therefore, it will make the surface scattering become heavier, and it will reduce the electron effective mobility. Thus, our leakage current will become higher. Next.
Okay, impact ionization. Due to high electric field, the electrons have higher energy and moving faster. Electrons with large energy are known as hot electrons. These hot electrons impact the drain, dislodging the holes that are there is swept toward the negatively charged substrate. This causes substrate current to happen and eventually increase leakage current. This is known as impact ionization. Yeah. Next, hot carrier effect. The term hot carriers refers to either electrons or holes that have gained a very high kinetic energy after being accelerated by a strong electric field. In MOSFET, the short channel device always have an areas of high field intensities from the potential difference between drain and source. With the high kinetic energy, these hot carriers are able to get injected and trapped into the areas of the device that they should not be. Device 3 has the highest leakage current due to its short channel length. It's impacted by short channel effect the most. This phenomenon can be reduced by reducing the doping in the source and drain regions. This can reduce the electric field across the MOSFET. Next.
So at last, actually, we also observed the punch-through effect on the devices, especially on the device 3, due to its shortest channel length among the three devices. So the channel length modulation will result in the punch-through effect that observed on device 3. The channel length modulation will cause the depletion region around the drain and the substrate to merge together, which form the single channel that underneath the gate. The depletion region that underneath the gate will result in the gate greatly depends on the drain source voltage, and increase the drain source voltage will result in the dramatically of the current. So the solution to resolve this punch-through effect is to increase the substrate doping. So that's all from for our presentation. Thank you.